Okay, so I guess I'm done setting up my stream. Let's see. Okay, so I guess I'm done setting up. Okay. So what I want to do today, I haven't been able to create a video in all of January. My other work stuff going on has been too much. So, and now I have to create a model of soil-pile interaction for research, and so I'm going to take the chance to model it live so you can see how I do it. It's a raw video. I haven't planned any of this, so it's probably going to take way longer than it should for a YouTube video, but in any case, here we go. So just so you know, I'm going to be working off a paper. I want to model a paper, one of my last papers that had a soil and pile model. That's what I want to model today. So let's see if I can find that one under my projects folder. And yeah, it should be this one right here. Okay, so I want to repeat this model. I want to upgrade the model from this paper. Which is this pile, and then it has a little structure on top which is meant to represent a offshore wind turbine. Okay, but for now I'm just going to set up this soil pile interaction model, and let's see where that takes us today. So bringing up Gmesh to OpenSees, we are gonna wanna create a Gmesh model. So, and the other thing I wanna do is I wanna upgrade this to use my new 10-node tetrahedron elements, which are pretty nice for soil problems. I can see some people in the chat. Hello to anyone who's listening. Okay, so let's, I'm just gonna go with a new folder for this. Let's go in the Dropbox projects. And then in here, I'm working with Davide Gorini, coming up with this new model. And let's go in here, new OPS model, and create this. And I think I have this folder added. No, here we go. So G2O, new OpenSees model, and I'm gonna open this folder, I guess. Open a terminal, yeah. So Gmesh, let's go call it soil pile.geo. Here we go. We have a blank Gmesh model. We're going to start with this. So let's start pretty basic, pretty simple, but I need a domain. And just like in the paper, I'm going to be modeling half of the domain to take advantage of the symmetry conditions for this problem. So 30 meters by, or I guess 60 meters by 30 meters, half of the domain. And we'll see where we go from there. That should be pretty easy to set up in Gmesh. So the way we'll go about it is I will add a box. So just a random box. Let's make it the size that we need. So let's make it maybe, let's start at minus 30 and 0, and in Z, 0, and we'll go 60 in the X direction, and we'll go 30 in the Y direction, and I forget, I think it was 30 in the, minus 30 in the Z direction, like so. Let's just, and this just destroyed everything, right? So 30, 0, 0. Let's just add this box and see what it looks like. So it's a little box, 30, 30, 30. The paper demands for a 30 by 30. And I have, okay, also 30 meters depth for the model, so it should be, I think this is right if I enable the axis. So it goes from minus 30 and 30 in the X direction, and I'm getting, yeah, I think I want to make it, so this is 0, the Y direction is the reverse, so this is what I want to do, 0, 30, X, Y, and Z. And I can just go ahead and mesh this thing, but this is not exactly what I want. I want the pile to be there, right? And I want, yes, let's have a pile there. Now that pile The way this model is set up is there's soil inside, and then the pile is just this thin little shell of elements. So do I want to model that with shells directly? Probably, yeah, right? I do want to model that with shells. So let's try that out. So I need a cylinder. I need that cylinder to be chopped in half. So let's add a cylinder. I'm going to close my door because there's some noise coming out. Like this. Okay, so let's add a cylinder. Where are we going to add this? Center base 0, 0, 0. Our radius today is going to be 5 meters and depth is going to be 20. So again, 0, 0, 0. This changes because I don't have the freeze X, Y, and Z options set up. So the axis DZ, this tells you which way the cylinder gets oriented. You can see it oriented in the X direction. I want to change this to be the Z direction, like that. This is what we look like. Okay, and we can embed that 20 meters into the soil. So we're going to need 20 meters down, and we need a radius of 5. So let's set the radius to 5, and the I guess this DZ tells you how deep it should go. Yeah, that's it. So that's the cylinder size. Let's embed that 20 meters into the soil like this. That's the cylinder we need. And then we have a radius, and we want to chop that off by half. How do we do that? So we can play along with this angle here, probably. Yeah, that's exactly what we need. That was simple. Okay. It might have ended up being the rest of it. Okay, so let's add that cylinder. There we go. Now, right now, if I mesh this, actually Gmesh crashed on me. So let's see what happened. Let's, I'll take a look at the GEO file. And for some reason, the terminal is staying on top of my Sublime text. So I should have the geo, yeah, this. So let's go back and take a look at the model. That's what it looks like. But I don't know why this terminal is persisting on top. So let's get rid of that, and maybe here we go. So these are two, I guess, independent volumes. If I take a look at the volumes, let's see, geometry, visibility, volumes. Yeah, those are two independent volumes. So the meshes, they don't mesh together actually. So to get them to mesh together, we will apply some things over here. So Boolean, let's say, was it the fragments tool? So let's go this E, select this, fragments. If I do that, I think it merges the model, maybe not. And Gmesh is acting weird again, so let's just go back in here. Now I added this Boolean fragments command. If I mesh, yeah, you can see after that Boolean fragments command, the meshes coincide. So let me just quickly show you. If I go here and I comment this out, and I reload the mesh with 0, and I mesh, you'll see that the meshes do not conform, the cylinder and the soil domain outside. If I enable this Boolean fragments command, and it takes as an argument the first volume, and as a tool the second volume, like that. If I enable reload, I get a conforming mesh. I get two meshes that are joined together, with which I can model my pile. Now, let's add a few more things. So the other thing I want to do is I want a second order mesh to use the 10 node tetrahedron, so high order mesh. Let's go over here in the meshing tool, and we can select the order to be 2. So this time, if I do, before I do that, let me just show you the nodes. You can see these are standard tetrahedrons, so you have 4 nodes per tetrahedron. If I now enabled the second order meshing over here, so if I go 1 and then 2 and 3 to mesh in 3D, you see that now the tetrahedrons actually mesh, and you have the intermediate nodes coming up. Now, there's some other things we can do here. We can enable some other things. So, quality of tetrahedra. What else do I want to do here? There's some optimize quality of tetrahedra, optimize high order meshes, aspect, high order element subdivision. So if we, if you set this, so if this is set to 2, I guess this was the default. This kind of looks like a quad over there. If I set this a little bit higher, you'll see the second order. So this is just one tetrahedron that has a curved side. So that's nice. It's still, even if you don't set the visualization to this, the mesh is still a high order mesh. So the element is actually following this curve as best as it can. It's just that you're not seeing it, so you don't have subdivisions here. You just have 2 subdivisions per element. So you're not resolving that curvature. But if you want to resolve that curvature, you can set this number a bit higher, maybe to 4, something like 4. And then you'll see the actual high order or the curvature of the element along that side. Let's do something. So let's specify some physical groups. So I'm going to go, geometry, physical groups, add. So let's I'm going to disable the mesh for a little bit, or go back to just a 1D mesh. So let's add a physical group for volume. So let's call this soil exterior. And I'm going to select the exterior volume, press E to create that. And we're going to have the soil interior to be this over here. And here we go. Hey, we got 4 people watching. That's amazing. That's incredible. Who are you people? Hi. So we'll continue with this model. What I wanted to see is enable visibility, Control-Shift-V, and I want to see the soil interior. And if I mesh, this is what the interior looks like. Now, if I change this, it looks really bad when I have low high order element subdivisions, so it looks like this. But the mesh is actually high order, so I don't need to set this up for the mesh to actually be better. If I set this to 3 or maybe 4, it looks like a cylinder. And that's the advantage of these high order elements, is that I can follow the pile geometry better, and also the advantages regarding the stress field, which is the main reason I want to move into 10 node tetrahedrons for this model, because I'll be able to resolve the stress field way better. Let's do a few things here. So I want to parametrize this model. So I'm going to be doing a parametric analysis with this model. So what I really want is for it to have some parameters. Let's do it as follows. So maybe you can learn a little bit from this. If I go here and I add, where was this? Define. I want to define a parameter, but where are those defined? It used to be the case that you could define them directly on the menu here, but I don't see it. I do not see it right now. Add parameter. Yeah, here we go. So let's have a parameter that is the radius of the cylinder. That's going to be one parameter. It's going to be 5. And yeah. So this parameter defines a variable. Parameters are, I can move this up here in the script and then start using it as a variable in here. So here where the 5 is, in this 5th parameter, I'm just going to change that for R. And now if I go ahead and reload this script, we reload it. Now we have this fancy parameter here. So I could just interactively change here the size of the cylinder. That's pretty neat. It's fun when you want to generate more than one model. So we'll replicate this idea, and we'll make some more parameters. So I'm just going to copy and paste here the command to create a parameter. We'll have, so duplicate these lines, and what I want is the length in x of the domain. So this is going to be lx over 2 in this direction and lx in this direction, so I can play around with the length in the x direction. And then what else? No, so I guess this is lx, and this is going to be 60, like so. And this is going to be the length in the y direction. So let's duplicate this parameter. Let's call it ly. In the y direction, we're going to have 30. We're going to start in 0, and we're going to do ly. And then in the z direction, let's have a parameter called lz. It's going to be 32. So we need that lz to be here. And we should be able now to play with the domain size. So let's go over here and reload the script. Now we have the parameters for the domain size, and we can tweak these to be whatever we want. Actually, you can drag and the domain will adapt. So that's nice. Who's watching? David Abadias and When Engineering Meets Tea. Hi everybody. I will also share the files on GitHub afterwards. So Jonathan, hello Jonathan. This is weird. I wasn't expecting people to show up, but hey, here you are. Okay, so I will share these files on GitHub or something later. Yeah. So we set up this little box, and then I want more parameters. I'll want a parameter for the cylinder, I guess. So the depth of embedment of the cylinder, that's going to be another parameter. So D, let's call that D. And that should be this value over here and this other value over here. Those are, I guess, all the parameters I can set up for now. There we go. But the pile disappeared for some reason. What did I do? I messed up this. There we go. So if okay, there's the pile, but the default value for D is 30. I should set that to 20. Reload. No, I didn't save, I guess. 20 and reload. Let's just close Gmesh and restart. This might, yeah, there we go. So I have this set up with some parameters. I have the same parameters right now that I had for the soil domain in my paper. So I have basically the geometry set up for this. Now I need some physical groups. I have some physical groups defined, so you can see Control-Shift-V, which brings up the visibility menu. You can see I have defined the soil exterior and the soil interior. Did I mess up? No, I didn't mess up the names. So the soil exterior is that part. Let's set the high order visualization again. Where was this? Geometry mesh. Aspect high order element subdivisions should be, it's not meshing high order because I restarted Gmesh, so there we go, that looks nice. So with high order and second order elements, we can see, yeah, that's a second order mesh right there. So I have the soil exterior and the soil interior. This is going to be soil, this is going to be soil, but I also need to add a little shell for the for the shell of the pile. This is a steel pile driven into the soil. So we're going to model that, I guess, using shell elements, but I'm not going to do that here for this stream, not for this one. But I can share the files. Because I won't do it now because it's going to be a mess. I'm going to need to subdivide these elements into triangles, into its subtriangles, and then create 4, I guess, shell DQKT or something like that. That's what the element is called in OpenSees. The triangle shell element that I'm going to be using for the shell. The other option is to, yeah, let's try that one out. So in this paper, what I had is the shells were modeled using actually the bricks, the same bricks, but disposed very thin, in a thin layer. I could do that here too with high order elements. But it's simpler to work with shells. I don't know, I could set up both models. It should be easy. Like let's have a thickness here. Thickness of the steel. We could do that. And then I can have a third cylinder like this, and its diameter is so the radius. This looks like a diameter. Let's call this depth, so that it's clear that it's the pile depth, and let's actually call it pile depth, like this. I keep messing up my cursors. Pile depth. That's a better name for the variable, and that's what I want to use here. Like that. And this is the radius. So the radius is going to be r plus the thickness that I want for the steel. It's going to be the third cylinder, and I should probably do a Boolean fragments with cylinder number 3 too. Now this is going to mess up my physical volumes, I think. So if I go here, yep, everything is messed up. And the thing is, my default thickness is 20. No, I should set it. Let's set it to 1 meter for now. 1 meter is still a lot, but let's set that to be that. 1 meter. So you can see that we have, yeah, these elements here. This is what I want, and let's just in case I lose my Gmesh, I'm gonna select the option here to save the model options. What that does is it creates this soil pile geo.opt file with all the options that I have. In particular, the element order. Where is this? Mesh element order is set to 2, which is the what I want for this model. High order element mesh. And you can see a whole ton of other options here that you can play around with. So it's nice to have this file and store your model options when your models start to get fancy. Okay, so we'll do this. And I guess my physical groups are destroyed, right? So the soil exterior, yeah, I need to recreate these. The soil interior looks fine. The soil exterior is this, soil interior. And if I select both, I guess I just need to add the cylinder into its own group. So let's go in here in the soilpile.geo, and I wonder what the volume number is for that. So let's go into let's just show everything, and I'll enable geometry volumes and volume labels. So oh, that looks really bad. Volume should be something like, yeah, there we go. So soil interior is physical volume 36. Volume 3, I guess it's volume 4, the one that I want to add into its own physical group, and let's call that the pile. That's going to be physical group 37, and it's going to be composed of volume number 4. And let's reload this Gmesh model, and now if I bring up the visibility tag, I should have the pile, and I can mesh, and that's steel. There we go. Nice. Awesome. Amazing. Okay, so those are the physical groups for the volumes, and then I need to set up physical groups also for the boundary conditions. So in order to do that, let's use the GUI. I'm going to go back into visualizing the interior of the domain, and I'll go here, physical groups, add surface. So I'm going to fix the X normals in this plane and this plane, and I'm going to fix the no, that's it. And I'm going to fix the Y normals here, and I'm going to fix the Z normals here. And here I need to specify symmetry boundary conditions. So that's the symmetry boundary conditions here. It just means that the Z normals are impeded, right? So it's the same as the Y normals are impeded. So it's the same as the other side, but I'm going to have it as a separate group and call it symmetry. There we go. So our physical groups have grown quite a bit. We'll see fix X should be the forward and aft faces, and fix Y, let's select these two. It's going to be the back. Z is going to be the bottom, and then the symmetry conditions is going to be here. And this is why you need to check this, because now I have a hole here. I need to add more stuff into this physical group. I need to add surface symmetry. I'm going to add this face, this little face, and nope, mistake, undo, U to undo. There we go, and we've added that. So now, I think if I select symmetry, yeah, I get the whole face. I get everything. So let's go back into the list. And what else do we want to add? I probably want a physical group for the pile over here. Okay, so let's call that the mud line. Pile mud line. The pile could protrude a little bit out of the soil, or we could have a separate cylinder coming up. Anyway, I'll add the mud line or pile mud line, and I'll select this face, and that should be it. And now I can mesh. Let's set the high order visibility. Mesh visibility, where was this? High order element subdivisions. For some reason I'm getting a weird subdivision there. Okay, because I get that element, that's one element, and that's another element. This looks so strange. But probably if I go for a finer mesh, let's just quickly set the element size factor to half of what I have right now. Yeah, that looks better. I guess it was just an artifact of the fact that I just didn't have a very thin or a very fine mesh. But this looks about nice. Statistics, I have 7,000 tetrahedra, high order tetrahedra, and that is about 100,000 nodes, which is quite a lot, but not that much. With parallel, I can probably get away with running this model. Okay, so let's end this by going over to OpenSees and using this. So I'm going to save this mesh for now, like that, and let's go over to OpenSees and see what we can do. Then I'll need to alter the thickness of the shell of the pile so that it makes some sense. I can also play around with using a structured algorithm. So if you remember this model over here, there's a structured mesh, and in that case I have a finer mesh near the pile, and then the mesh gets bigger as we move away from the pile, and that's best managed using structured mesh, even in Gmesh. So I'll do that later. First I'll make sure that my OpenSees model is working. So let me check the chat. David has to go. Yeah, okay, that's fine. He's asking me to define planes of zero thickness element. Yeah, this is something I'm going to need for this model, so I'll do that later. Contact shell to interface. So yeah, that can be done with Gmesh. So I'll try to do a tutorial of that sort in the future. I'm going to need contact elements in this model anyway, so I'll set it up for this model too. Okay, anyway, let's move over to OpenSees. What do we have in OpenSees? and get rid of those comments. So I'm going to start off from one of my tutorials. There's some vibration noise coming on the back of my office. Okay, so let's start with this example 2. Yeah, I'm going to start with this example 2. I'm going to copy it to that other folder that I was working on, which should be projects, team, new OpenSees model, and let's just call this pile or soil pile. I like to name the Gmesh files the same as the Python files I want to run them with. So it's going to be called soilpile.py. And we're going to modify this script to take in this mesh and see what happens. So first off, we import OpenSees as OPS. This doesn't work in most systems because if you download OpenSees PY using pip, or you're on Windows and you have some other setup, this is not how you would run this. Okay, so this is specific for my system. I'm importing Gmesh to OpenSees, and I'm importing Gmesh, and I'm going to initialize the file that I just created. So it's going to be called soilpile.msh, like this, and I'm going to create a basic builder with 3 dimensions, 3 degrees of freedom, and we're going to start off with a single material model. This is set up for steel. Let's set it up for something closer to soil. Now, to get proper parameters for soil, what would be a good Young's modulus for soil? What would be a good Young's modulus for soil? I'm just going to go, you know what, I have another model that goes with this one. So I can probably get that from here. New OpenSees model, no, this is not what I want. I want project, edit project, and I'm gonna add the whole folder. So I have the old OpenSees model that I want to base this off. So this, yeah, I have a G0 here. I can use, and new is set to 0.3, so let's use G0 equal to 1.25. Okay, no, this is a bit cumbersome, but okay. Modeling a pile like this one. Okay, so the value of E, so G0 is 125. That means G is going to be G0 times whatever the pressure is over the atmospheric pressure, something like this. It's usually with a square root. Import numpy as np. So I want to use np dot square root over here, and the atmospheric pressure, it's about 100 kilopascals, if I remember correctly, atmospheric pressure. At sea level. At sea level should be 1013 what? What is it in pascals or kilopascals? So 101, 325 kilopascals. So 101, 101, 325, and this is in the units of kilopascals. So my model is going to be in kilopascals. Actually, let's move over to pascals because I like standard units. And then let's pretend P is going to be like 3 atmospheres, like that. So then I have G, and I'll have new set up to 0.03. 0.03. So then I can work back what E should be. So E should be G is E over 2, okay, so this should be G times 2 times 1 plus the Poisson's ratio. So I can set up this material to be that. I don't know why this stuff is here, but I'm going to get rid of it. Rho, that's a bit large for soil. Let's have 2,000 kilos per meter cubed. G is going to be that. So we have a elastic isotropic material that is representative of soil. So let's call that soil mat tag. So that's going to be the first material. E, nu, and rho. So then what? I can add the nodes from the mesh by selecting with this function. I can select the physical group that I want to add nodes from. So let's our physical groups in this case are soil exterior, soil interior, and pile. Let's add all of them. Do I have a function to add all nodes in Gmesh to OpenSees? I might have, because that would be a smart thing to do. Get all nodes. There, I think this returns node tags, coordinates. So I should be able to get all nodes and add them to OpenSees. Let's try to use that. So G2O dot get all nodes, and that should take in the Gmesh model. That's a model I just created. Gmesh, no, that should be Gmesh dot model, and it's going to return for me the tags, the coordinates, tags and the coordinates, tags and the coordinates. All I need is a tag, because I'm going to add the nodes to OpenSees using these node tags. So let me add an exit 0 here and try out this script. For now, all this script is doing is adding nodes. Okay, so I have an error here. This is a comment got uncommented. So this is what I mean. I need to go look for my OpenSees library. So in order to do that, I'm going to import sys and sys.path dot append. So I'm going to append to my path the location of my OpenSees library. So it should be home/jable repositories OpenSees and build. And there, it's running. At least it's not giving me any errors. So till now, what we have accomplished is we have a mesh. We have a mesh file. The mesh file I'm using is this huge file over here. And I'm going to be adding the nodes. This is just adding the nodes. That's all I'm doing. Now let's go for the elements. So I'm going to add, for now, 10 node tetrahedrons. 10 node tetrahedrons. So for that, I'm going to need this line over here. So this line says, get me elements and nodes in a given physical group. So what physical group do I want? I want the soil exterior, for example. Soil exterior. And then I'm going to be adding in a loop all the elements that I get from the soil exterior in as 10 node tetrahedron elements. Let's see if this works. Here goes nothing. Okay, so solid material tag was not defined because it's actually this tag, soil mat tag. Let's see what happens. Okay, so that worked. I've actually added the elements, and if I go ops.print, I guess, or print, what's the command for printing the model? Print like this. Does that do anything? No. OpenSees, let's see. OpenSees documentation. You would think that I would know this, but I don't. OpenSeespy. print model. Yeah, it's print model. I keep forgetting these commands, but it's okay. It's easy to look up. So just want print lowercase and model. Like this, I should get a huge output with all the nodes and elements I've added. Okay, here we go. So let's continue. Let's add some more elements. And to add more elements, for some reason I was storing the tetrahedron element tags. I'm going to avoid that for now, but I'm going to duplicate this and call this for the other soil interior and the pile physical groups. So soil interior and the pile. The pile, let's make it steel right away. So I'll add my second material. Second material is going to be steel. Steel is going to be material number 2. Let's call this steel mat tag. I'm just going to need yield, Young's modulus should be around 200 gigapascals. Did I get that right? If I didn't, let me know in the chat. But our row should be like 7,300, something like that. For now, it's not that important. I don't know why I have this G constant, but I'm going to just throw it all the way up. Get rid of that. So now I have the steel material, and all the pile elements are actually going to be using the steel material right away. This is why, because I'm adding the self-weight as rho times G. So let's do as follows. This is going to be rho for soil, right? And I'm going to have a separate row for steel, 2 different variables. I don't need to store the E and the nu, but these 2 groups are going to be row soil and row steel. Let's quickly check that this is running. It is running. So then what? Let's fix some nodes. So for the group that is called fix X, I'm going to literally just fix the X nodes, and we'll repeat this pattern for the other physical groups. So fix Y is going to get fixed in the Y direction like this, and then fix Z is going to get fixed in the Z direction. And I have to remember that I also have the symmetry condition, the symmetry group. I want to have that, the symmetry is going to be fixed in the Y direction. So that's called symmetry conditions, symmetry. And that one is going to get fixed in the Y direction. This should be working for now. No errors, so far so good. And then time series. Okay. This is why I needed the tetrahedron element tags. Okay, so let's resuscitate. Okay, so I need to store the element tags for all tetrahedrons. So let's do that. Let's say tet element tags is going to be element tags. And then I'm going to append to this list. Append the element tags. These are the element tags that are going to come from the soil interior. And I'm going to append element tags from the pile. I should get, after this, I should get a large list of all the element tags. Element tags, sorry, these were called tet element tags. Let's run this real quick, so I'll get a huge list. List. There should be, but why am I getting 2 braces there? I'm not okay with that. 1 brace and then because if I just add the element tags from the beginning? Like this, I get one list. Okay. The thing is, I don't like the fact that from some point onwards, what I'm getting is a list embedded in another list, so it's not working exactly as I want. Where is that brace? What if I do, instead of append, or maybe it's just going to work. Is it just going to work? Because the tet element tags, you see, this is like two lists. It didn't append the lists. It just created a list which has a whole bunch of integer numbers at the start, and then at some point there's a list that is appended here. There's a brace. So int, and then a list of ints, and then another list of ints. So I could probably hackily fix this if I do it like this. 0, 0. Ah, I'm using append and not concatenate. Okay, no, that's the problem. Okay, no. Undo, undo. And I don't want to append, I want to do plus equal element tags. Like to concatenate the two lists. There we go. That's what I have. Sorry, some Python hiccups here and there, but now I have a nice list with all the tetrahedron elements, and that is needed because I want to add self-weight load to all of those elements. So all the elements that belong to the tet element tags list will get a self-weight load of with a factor of 0.001. Now that factor ends up being this weight multiplied by this number. So these two things. So that's how I can have different densities in different parts of the domain. All the elements that belong to soil physical groups will use rho soil times G, whereas the pile elements will use rho steel times G, which is great. And so I have this one command that adds the self-weight. And now let's do a linear analysis and visualize. I'm going to get rid of this loop, which was supposed to show me the displacements of all the nodes on screen. I just want to go back into Gmesh and take a look at the results. It is computing, and it's a large mesh, so it's going to take a while to do one step. It's going to take a while to do one step. And let me bring up system monitor. There we go. It finished. It took a while, but it did finish. Now the displacement look horrible. Let's see what happens. Okay. No, that doesn't look okay at all. We'll see why. So the post-processing view, we have the aspect. Oh, my displacement factor is huge, but still the results are huge. 10 to the 4. I'm not okay with 10 to the 4, so let's go for 0. And let's take a look. Alt-M to get rid of the mesh. Yeah, the boundary conditions are being enforced at the bottom, I guess. It's all moving in the correct direction, and the boundary conditions, I think they're being applied. Now this looks fine, except the scale is bad. Like, no, you don't want displacements to be 1.17 times 10 to the 4. But other than that, the solution looks fine to me. Let's see what's going on. And before I move on, I'm going to remesh this, and I'm going to go for this coarser mesh so that the solution doesn't take so long. So let's rewrite the mesh file. It's less elements, so it's not going to take us long. Now, what did I mess up here? What did I mess up here? So maybe the soil was too... Let's go for 10 atmospheres of soil stiffness. We're on base units. Steel is 10 to the 9. (200 kilos per meter cubed). Did I get this right? The E value for the soil. I'm just going to quickly print E. And this should be in pascals, just so I can take a look at what values I'm getting. Yeah, no, it's a low value. Very low value. 10 to the something pascals. Yeah, I messed up this. Soil value is very low. Because this should have a... Okay, that's why. This should have an atmospheric pressure here, apart from this. I think that formula... Let me steal it from OpenSees, actually, that formula. I know that formula. I'll quickly switch to my OpenSees Sublime project, like this, and I'll go into Sunny Sand MS, and let's take a look inside the function get elastic moduli. So this one, so it's the G0 times the P atmospheric times square root P over P atmospheric. Ignore this because it's a dependency on the void ratio. Yeah, but that's pretty much, so I'm just assuming this factor over here is 1, which is not totally correct, but okay. Well, we can incorporate that. If I know what the, let's go back into the other project, Gmesh to OpenSees. I do know what the E0 I'm supposed to be using for this is, so the OPS model, it should be in this one. E0 should be 0.785. So let's incorporate that actually. E0 0.785. I forgot the number. I have no memory. Okay, and the little piece that of code that takes care of that should be this 1 plus E0. And then I have to the square 97 minus E0. That should be the piece of code. Let's go back to about 5 atmospheric pressures of depth. And I messed up my syntax. E9, this is E0. So that's the original. Okay, now we're good, except the amplification factor is too big, but we can get rid of that. So I need an amplification factor of about, what? No, it's still too big. So this is self-weight, just self-weight. If I go for something like 200 there, it starts looking okay. And let's draw element outlines. And aspect, do I have the option to make the high order elements look nicer? Not in the post-processing view, I guess. High order, where is this? Visibility. So you can't make the high order elements look nice in the post-processing view. Alex Petalas, are you there, man? Really? What? Okay. So this is the... You're there, Alex. That's amazing. What? Okay, so this is the mesh. This is a high order mesh for this soil pile, but I can't see the pile in high order, so it doesn't look as nice as I'd like to. But that's okay. This is looking fine. This is a nice mesh to get started with doing some more stuff. And let's do some more stuff. So let's maybe to the top elements, I could add a load just to get the pile embedded a little bit more. So you see the application of the gravity stage, because the pile has a larger stiffness than the surrounding soil, and I am applying self-weight and everything together, so then the soil that is inside the pile doesn't actually deform as much, so then you get the pile sticking out a little bit. This is all elastic, Alex, but then I'm going to switch over to something, a fancier constitutive model. I think this is what I want. Let's add a little load somewhere else just to see what else we can do, but the thing is, I don't have a good way to apply a load at this point. I should add the monopile and then create the links and then use that to apply the load. But I need to do some more meshing and some more stuff. I think I'm done for the day in terms of what I want to do. I'll just add a little load for you guys to see what else can be done. So let me get the mesh node label. I enabled all the labels, so this is gonna be huge actually. No, I don't want this. Okay, in this mesh, you see here it looks a bit nicer. I have few elements here, so that's why I don't get a nice view over there. But what I want to do is I want to get the the node numbers for some node over here, so I can apply the load. Node labels. Let's actually just keep the mod line. So let's add a load to node number 135, like that, and then do another analysis. We'll just stick it further into the soil, or maybe we'll push laterally for 135. Let's do that so that you guys can figure out how to move on with this. So this is static analysis, and after static analysis with a constant load, I'm gonna create a second step of analysis, a second stage, a new time series, and let's go for a linear time series in this case, and the pattern tag is going to be 2, going to be a plain pattern tag, and no, we're going to add a load, another load to node 135, and we're going to push in the x direction with some large number like this. We're going to do another analysis step and visualize the results. The displacement factor I was using before was something around 300, I think. No, I don't have it handy. So if I run this model now, step 1 and step 2. What am I getting? I think I can see a little bit of sideways motion. Aspect, visibility, element, yeah, it's moving laterally. So that's how you add a load. We could probably animate this if we borrow code from my other tutorial. Let's do that, just for fun, just because we're here. Let's go in one of the latest tutorials. I guess I was doing that. Example 4 maybe. Yeah, this is the code. So I want a for loop to apply the loads, and then you visualize in the same group. So let's start with a linear. Before I do that, I probably want to ops.set time to 0 and ops.load const. So keep the loads from the previous stage, reset the timer to 0, add this pattern, and then the load control. I am actually going to switch the load control a little bit. Before I do this, I'll do it in 10 steps so we can get a sense of how the displacement grows as I apply it. So Merlin Lashram says, I've gone through your wonderful videos, helps me to clear my doubts. That's great to hear. And then it would be great if there's a class to cover how to use the 4-node quad elements connected to viscous absorber at the boundaries using zero-linked elements and duplicates of nodes at the boundary. So you want to do Leismer-Kuhlemeyer dashbots. Yeah, maybe I can set up something like that. I've done some propagation work in the past, so something like what the people at SDKO do for their software. I could definitely do that, but it's going to take me some time to get there. I'm actually doing this video because I had no time to do anything, so it's just a way for me to get some content out there for you guys and get my research going. Anyway, so we're going to move on with this integrator load control. We're going to do 10 steps. A nice way to do it is set a variable. I'll do n steps. And then analyze it. It's a static analysis, so I don't need the second argument. But then we're going to visualize the displacements in Gmesh after that for each step. The first step is going to give us the initial state before at the end of gravity. Let's bring that all the way up here. Unum step 0. And we're going to start here at step, we're going to be calling them these step +1, just so that it doesn't get confused with the gravity state. Okay, I think this should be good to go. Let's try it out, and then I'm going to end this stream. All these steps, it's pretty fast. Remember, these are second order elements, so you don't need as many as in the case of tetrahedron elements. Okay, so this is our step 0. Get rid of the mesh. Enable visualizing element outlines, just because I think it looks a bit nicer. You might or not agree. And let's animate. Yeah, you can see that moving sideways a little bit there. So there we go. That's soil pile interaction with a little bit of steel. If you want to do nonlinear soil, there's more considerations that you need to take care of. So for example, you would switch, instead of using elastic isotropic material for the soil, this one, you would switch to something, I don't know, some like Mansari Dafalias or whatever you want to use. But then you'd actually add everything. You actually need to take care of the construction stages. So you would add everything as if it was soil to start with, and then you would replace the soil elements that belong to steel with the actual steel, and then do some nonlinear iterations there, enable plasticity everywhere, and then move on with your analysis from there. So it's a bit trickier to set up a model like that. And I'm gonna have to do it now for this research, and I don't know if I'm gonna stream it, but I definitely know that I need to do that. For now, this is all I wanted to show you guys. Thanks for the company. It's been amazing. Like 9 people at peak. So I'm just, I didn't know I would get this amount of attention, and I'm happy too. So if you guys want something, just write me. You know where to find me. Like and share, and I don't know, all that good stuff that will encourage me to come up with some more content. See you till next time.